Okay, let's get started. So from last time, we introduced these cylindrical coordinates. So let's kind of sketch out what these cylindrical coordinates meant on an ordered triplet in R3. So if I had some point here, P, we said that it had an R, theta, and a Z component. And that meant that we would measure how far it comes from the xy plane as a Z component, and then we'd use polar coordinates on the shadow that it casts onto the xy plane. So if we had our x-axis here, and our y, and then our z, the angle from the x-axis is measured as theta. This length here was measured as r, and then the elevation we called z. Now, we also did talk about how it was completely arbitrary for us to pick z as being the Cartesian variable that made it through, that z is equal to z, right? And we chose polar coordinates in the xy plane. You can do any combination where you can do xy is polar, and then your y is your elevation, the remnant from Cartesian, or you can do, y, z is your polar coordinates and have x just be x. So you can do any combination like that, but most typically you'll see it cylindrical coordinates being that z is equal to z and x and y are into polar coordinates. Okay, so now let's start talking about integration. So let's suppose I have some domain E that is the set of points x, y, z, such that the ordered pair x and y belongs in some domain D, but z is bounded by a function below and above by x and y. The triple integral we can write over E of f of x, y, z dv, kind of like how we've seen yesterday, a little foreshadowing. We have our double integral over the domain D, and then we have the z integral with bounds u1 and u2, both functions of x and y. Now, this was nothing really new. This is how we kind of discussed triple integrals in the first place, where we had this extra third integral, and then we have a projection down to this region D, and then that's how we dealt with double integrals. So perhaps Cartesian coordinates aren't the best for doing integration on D, right? Perhaps maybe we can express D in polar coordinates. So perhaps it's best to write D as the set of all points r and theta such that, and this is just an example, we can have that maybe alpha and beta are bounds on theta, and then maybe we have bounds on r that are functions of theta. So that's one example. So it's perfectly fine for us to do this, right? This is cylindrical coordinates in essence, right? I'm doing a z is equal to z. So I do that first integral. And then my projection is in this region D, and I'll just express D in polar coordinates. So I will eliminate Z via this first integral, and then I'll sub in these functions of X and Y, but then I'll have to convert all of the X and Ys that I have into polar coordinates as well. So if I have that this is my region D, just for an example, perhaps I can write this triple integral out in its full form. So we have E of f, x, y, and z dv. Given that this is how we can write our domain D, maybe this is alpha to beta, h1 of theta to h2 of theta, and u1. We have to write this a little bit differently because now we're in polar coordinates. So we have r cosine of theta, r sine of theta, and u2 r cosine of theta, r sine of theta. And then I have my function f with r cosine theta, r sine theta, z, then dz, dr, d theta. But I still have to remember, if I'm doing polar coordinates, remember I have this extra r in here. So I'll put the extra r right there at the end. So that still follows it, remember? So dA was either equal to r dr d theta, or maybe a dx dy. Right, so we have that extra r in there. Okay, so let's do an example. Let's try to do a triple integral in cylindrical coordinates. Do a little bit of a word problem. We're going to find the limits of integration in cylindrical coordinates for integrating the function f of r theta z over d. Bounded by, or below by, c equals 0, laterally by the circular cylinder x squared plus y minus 1 squared is equal to 1. And above by the paraboloid z is equal to x squared plus y squared. Okay, so let's kind of get an idea of what this thing looks like. First thing we're always going to do is try to do a rough sketch. So we're bounded by the z equals 0 plane. So we're on the xy plane down here. Then we're laterally confined by the circular cylinder x squared plus y minus 1 squared is equal to 1. So this is just a circle in the xy plane of radius 1, but it's offset a little bit. It's centered at 0, 1 instead. So let's try to see if we can draw a little circle here. Let's kind of do something like this. And remember, because it's centered at 0, 1 on the x plane, it does just touch the origin because it has radius 1. And then we're bounded above by this paraboloid, this x squared plus y squared. And that kind of looks like, so I want to do a bunch of arrows. You know, something like this. Not quite symmetric, my drawing, but it should be. Something like that, right? And now, if that's what bounds it from above, let's kind of just draw some lines up. Maybe, well, actually, let's do some more circles here. Make it maybe a little bit wider. So something like this. So it looks like a cylinder just got sliced by this paraboloid surface. So because the top is bounded by this paraboloid, laterally, the most that this thing is going to achieve is the cylinder itself. So we know that the projection of this object onto the r theta plane or the xy plane is going to be just that unit circle, just a little bit offset from the origin. So it looks to me like this is a prime candidate to have my cylindrical coordinates, as well as selecting my xy plane to be where my polar coordinates are, right? So if that's what I'm going to do, then what we're going to do now is continue to sketch, but now we're going to kind of sketch in cylindrical. And the first thing is I'm going to draw the projection. And we've done this before, and we should always do it, is just draw the projection out. And I know it said it was a circle, but just for sanity's sake, let's go ahead and make our circle here. So it's a circle, radius 1, offset right here. So this is y and x. There we go. This is the y-x plane, and this is our projection, which we were calling D. But it's also useful to plot z versus the x and y plane, right? So if you're looking at it directly from the side, what does this thing look like? Well, you can think of x squared plus y squared as being this r squared. So you can also think of this, or you can just plot, this r variable in cylindrical. So z versus is equal to r squared. That's just going to look like a parabola, right? But we only get so far. The radius that we get out in this direction, because this is a circle of radius 1, is 1 to the center and then another 1 out. So we'll get a straight line somewhere that's cut by the cylinder that goes straight down here. At r equals, shouldn't be 0, should be 2. And we can write this as z is equal to r squared. So that's the side of our object. So now that we've done these sketches, we can kind of talk about the bounds to do this integral. So step 1. The z bounds are from z equals 0, the bottom, to z equals x squared plus y squared, which in cylindrical coordinates is just r squared. And we can kind of just look at our side view here, right? We can draw our arrows. We're going from z equals 0 all the way up to this curve that is z is equal to r squared. Now this object gets projected down onto the xy plane, and this is what it looks like. So this is looking at it from above. So step 2 is that the r bounds are defined by the projection that we have there, which is from the cylinder, or in the xy plane, this circle equation, x squared plus y minus 1 squared is equal to 1. So let's go ahead and look at this in polar coordinates so we can go ahead and make our substitutions. So first, we're going to FOIL this out. This is x squared plus y squared minus 2y plus 1 is equal to 1. Or we can write this as, since this is an x squared plus y squared, that's just simply r squared minus 2y, which is 2r sine theta. And then these ones end up canceling, or this is equal to 0. So if I need this left-hand side to be equal to 0, and I'm looking at my r expressions, I get two things from this, because you can easily factor this out, right? This is r times r minus 2 sine theta is equal to 0. Or that r is equal to 0, or r is equal to 2 sine theta. And if you remember from Calc 2, when you started talking about polar coordinates in the first place, you might recall that this, in fact, is the circle that we are describing there. Okay, so step 3. The theta bounds are defined by the values needed to generate a full revolution or draw the circle that we're defining as r is equal to 2 sine theta. So you need to be careful here, because you might think, oh, this is just a circle, so it should be 0 to 2 pi. Well, this function, we have to be a little bit careful when it draws this object, right? Because it might, when we were doing polar coordinates, remember it has that angle and then it goes out some set radius. Well, how much of theta do we need to actually make this circle out? Is it a full 0 to 2 pi, or is it something else? So notice that theta from 0 to pi or sorry, 0 to pi over 2 draws one half of the circle. So let's kind of look over this. If our function is 2 sine theta, it starts with a radius at sine of 0, which is just going to be 0. And then once it reaches pi over 2, sine is 1, and then this gets a radius of 2. So we look up at this circle, and let's kind of do it visually here. We start with a radius of 0 at the angle 0, but by the time we get to pi over 2, we've already drawn half of the circle, because this is now r is equal to 2. So theta from pi over 2 to pi draws the other half. So if you go back to our drawing here, I'm at pi over 2, and now sine is getting smaller until it reaches pi, which it finally gets to 0 again. So it only takes 0 to pi to draw this object. If you went ahead and you started going past that, what happens? So if you're in the direction of pi and then now sine is negative, what ends up happening is it starts drawing the circle all over again. It's this angle, but it's a negative radius, so it comes through and it ends up drawing a second time. And you might recall this from Calc 2. So we have to be careful, right? When we're dealing with functions of theta, it's best to kind of just systematically go through and think about what this is actually drawing. So if we set our integral from 0 to 2 pi, we would be drawing this circle twice. And what's end up going to be happening there is we're just going to be doubling the volume, which we did need to be doing. So step 4. Our triple integral over the region D of f r theta z dv is the triple integral from 0 to pi, from 0 to 2 sine of theta, and 0 to r squared of f r theta z r dz dr d theta. So that was how we kind of broken up this problem into kind of figuring out what these theta bounds are. And I cannot stress enough plotting things like this. Try to make a sketch of what's going on. It might not look pretty, but definitely sketch what the projection looks like. Sketch maybe a side view of this, especially when you're doing cylindrical, or later on we're actually going to talk about spherical. Perfectly fine to do this as well, because it kind of gives us a visual aid to figure out what the r bounds or the z bounds will be. Now, we could have done this problem a little bit differently. We didn't necessarily have to do dz, dr, d theta. We could have done maybe dr, dz, d theta, and these pictures would change a little bit. For instance, maybe if we did dr first, we would have to draw the same picture, but we would have horizontal traces that go across like this. So we would have to go from, say, the square root of z out to 2. And the projection of this would be the box in the z theta plane. So it would be like, oh, how do I unravel this cylinder? So z goes from 0 to this point here, which ends up being 4. Yep, 4, 0 to 4. And then we need to unravel that whole cylinder. So in that case, it goes from 0 to 2 pi. So you have to be a little bit careful. But I think this is the easiest way to kind of think about it in this case, is dz, dr, d theta. But if you would like, try to rewrite this in terms of how to do this in a different order. Get some practice. Let's do another example. Let's find the centroid where a density is equal to 1. So remember, centroid just merely meant the center of mass for something that has uniform density. Of the solid enclosed by the cylinder x squared plus y squared is equal to 4. And then bounded above by z is equal to x squared plus y squared. and below by z equals 0. Okay. So doing a sketch of this guy, let's just do maybe, because we're talking about cylindrical coordinates, let's do a z versus an xy plane. So in the z versus xy plane, we have this function here. It's bounded above by. This is z is equal to like an r squared. So we expect to have a parabola again. Now this time we are bounded in the xy plane by a cylinder of radius 2, or just a circle of radius 2, so that extends in the z direction. So eventually we get these straight lines that come down from the cylinder. At r equals 2 and r equals -2. Most of the time, if the thing is symmetric around the z-axis, you only typically write just or plot half of this, but this is the xy plane, so we're drawing both sides of it. And then we're looking for this region here. So the projection of this guy, if we look from above, is still a circle. This is r squared is equal to 4, where that r is equal to 2. Right, because this was x squared plus y squared is equal to 4. So a circle of radius 2, centered at the origin. Great. Okay, so now let's set up our integrals. We need to calculate the entire mass. So remember, our density was equal to 1, so that's pretty nice. So our mass is equal to our triple integral. Now z was going from 0 up to this x squared plus y squared, which we can write as r squared from our diagram up here. Right? This is x squared plus y squared. Our r value goes from 0 to 2. And to draw this circle, we need theta to go from 0 to 2 pi. Our density was 1, so all we have is an r dz dr d theta. So this is actually a really nice integral. I'm actually just going to write out what it ends up being. This is just 8 pi. Okay, again, let's put our engineering hats on. Can we save ourselves some work? Think about this object for a second, right? It's symmetric across, or it's like basically mirrored across the x-axis and the y-axis, right? And it has uniform density, meaning that there's the same amount on each side. And think about it, it looks just kind of like a bowl, right? It's a weird flat bowl, but it kind of looks like a bowl, right? And if a bowl has uniform density, right, it's certainly its center of mass in the xy plane should be the origin. So by symmetry, we know that the center of mass, at least in the x and y coordinate, is 0. So we need to find the z bar. So to find z bar, we take a look at the moment across the xy plane. So this is 0 to 2 pi, because we're talking about the same object here. 0 to 2, and 0 to r squared. Now remember, we have an extra z in here, then an r, dz, dr, d theta. So again, this is just setting up. I'll go ahead and tell you what this integral ends up being. If you want some practice, you can check it out. This is 32 pi over 3. Now, a question you might have is, what if I was calculating a different moment and I didn't necessarily see that these were 0 and I wanted to calculate them for myself? So you would have either an x or a y in here, but we're not integrating with respect to x or y, so we would need to convert that into cylindrical coordinates. So with that, we know that the center of mass is 0, 0, and 32 pi over 3 divided by 8 pi, or 0, 0, 4/3. Okay, let's do one last example. Where we're going to look at the integral, or the triple integral, in Cartesian coordinates. So we have 0 to 5 in x. We go from negative square root of 5 minus x squared to 0 in y. And then in z, we go from x squared plus y squared minus 11 to 9 minus 3x squared minus 3y squared. We have an integrand of 2x minus 3y. So all we're going to do is just convert this, because this looks awful to try to do in Cartesian coordinates. So let's get some practice with rewriting this into a different coordinate system. So I find that it always helps to immediately write down the bounds. So we go ahead and we just rewrite the bounds that we have from our integration. Now, it's important to note that one set of these bounds doesn't necessarily mean one set of bounds for the other corresponding coordinate system. It might be a mix. So one piece of information might give us a lower bound for one and the upper bound for, say, another. Especially true when we start talking about spherical coordinates. It's not always 1-to-1. So we have to kind of get an idea of what's going on here. So let's look at these z bounds. The z bounds can be rewritten, because I see these x squareds and y squareds a lot. So we look at these z bounds, and I can write this as r squared minus 11 is less than or equal to z, which is less than or equal to 9 minus 3 r squared. Okay, that's pretty nice. So that might actually be our z bounds that we can be using for cylindrical coordinates. So the x and y bounds detail the projection. So remember, whenever we're looking at these triple integrals, the latter two are always the projection plane, right? So this details what the projection of this object looks like. Well, the projection, let's kind of just do a sketch of what's going on here. We have that y goes from negative square root of 5 minus x squared. This should kind of be a red flag to you, right? What does that look like? That looks like a circle, right? So in fact, you can write that just off to the side here, that this is, so we square both sides, and then we get 5 minus x squared, or we get that y squared plus x squared is equal to 5. So it looks like we have a circle of radius 5, but we have to remember that this goes from negative square root and to 0. So this is the bottom half of the circle up to the y equals 0. Okay, so first let's go ahead and draw just a circle here. So we know that we're already limiting ourselves in the y direction by y equals 0 down to the later half. So we don't even care about this upper half. So now let's go ahead and look at the x bounds. The x bounds tell us that x goes from 0 to root 5. So I don't have any negative x. And if I don't have any positive y, it looks like the only thing that I'm really kind of concerned about is this corner of this circle. So with that piece of information, I can figure out what my r bounds and my theta bounds are. Right? If I'm just talking about that quarter circle, I know that r goes from 0 to root 5, and I know that theta goes from 3 pi over 2 to 2 pi. So with all of this together, I can rewrite my integral as 3 pi over 2 to 2 pi. Then I go from 0 to root 5. And then I also have r squared minus 11, and then 9 minus 3 r squared. And I substitute in my values for in my integrand from Cartesian to cylindrical. So I go to 2 r cosine theta minus 3 r sine theta. Can't forget my r. Then I have dz, dr, d theta. And if you want to get some practice, I'm not actually going to go ahead and do the evaluation step, but if you want to get a little bit of practice, you can try this out. This is 200 over 3 root 5. Okay, and that finishes up our cylindrical coordinates section. So with that, why don't we go ahead and take a little bit of a break. There is a question, but I'm going to stop the recording here.